Welcome back. So in the previous lecture we discussed about the geomorphology of the active regions, and mainly we looked at the tectonic geomorphic features or the markers on the surface, and I was showing the example from central Himalaya, that is Kumaon Himalaya, where we were able to see some paleo wind caps or uplifted paleo channels of Dapka and Bow River. And let's go further what we identified from the trench and how we did and how we proceeded for the trench after identifying appropriate location. And this part I have already discussed in the previous lecture, that the best location to dig the trench is to identify the youngest landform which is displaced, and at the same time we also look at that if those areas are not been disturbed by any human activity. Even if the area is quite eroded, then you won't be able to pick up the signature, sharp signature on the satellite data, hence you will avoid those locations. But once you have identified after doing detailed field work that the appropriate site is good in terms of excavating the site and all that, then you can proceed further for mapping. So now if we look at the field photograph of the location here, then what we see is that we clearly make out there are two scarps. The front one is the younger scarp, and then you have the older fault scarp at the backdrop here, and the front side is your Indo-Gangetic plain. So we identified this scarp, which was the younger scarp, and after having detailed survey walking down along the scarp, we identified appropriate site for digging. And this was of course because in the forest area, so we were also concerned about that we are not going to cut trees and all that. So we identified the appropriate area, and before getting into the trenching part, we did GPR survey, which helped us in fixing up our trench boundaries. So this was the GPR profile. This is I would say that this is a raw profile what we took. This is not processed at all, but this is further we added the topographic corrections to this, as well as the slight processing part. So after processing, we clearly see the low angle fault cutting the deposits, young deposits, and since we until we are unable to open, we won't be able to say that this is young deposits. But of course, looking to the topography here, that was at least confirmed that this scarp is developed by displacing the young deposits in this area. So we were confident enough that whatever we are seeing is the near surface stratigraphy and has to be in young deposits. So finally we started opening the trench, and what we did cleaning in that part, everything I have, and what we will do after cleaning the trenches, will grade the trench and all that. So I'll just straight away move to the trench log, how we interpreted the trench in this area. So this is our photo mosaic of the trench, which was excavated across this scarp here, and which goes almost like about like 10 to 15 meters, and this is the topographic profile we have, and the trench portion has been marked by the dotted box here. And after mosaicing the photographs, you can prepare a detailed sketch, but this we did, as I have discussed right in the beginning, that we did the sketching of the trench precisely using the grid in field on graph sheet, and we demarcated different units in field itself, because that will help you in identifying the fault strengths as well as the contact between the different units here. So you can clearly match few units which are prominent, showing prominent contacts For example, this contact is very prominent here, and it is quite clear. We can see the structure within the gravel, which is folded along the low angle fault here. So after having detailed cleaning and all that, and after demarcating the boundaries between the different units, we mark the fault which goes right up to this point here. And of course, a few doubtful areas which could be the depositional or the erosional contact were been marked by this. One thing is very sure, that at places we were able to see a very typical notches which were been developed within the sediments, and this could be a result of bulldozing effect and the displacement along the fault strengths. So in this trench we were able to pick up two fault strengths, F1 and F2 were the major one, and since what we saw is that the F2 has displaced more younger units, hence we concluded that the F2 was the fault strength along which the most recent event took place. And stratigraphically, if we reconstruct the stratigraphy of the sediments which are deformed, of course, then unit A is the older one and unit H is the youngest one. So this is our topographic surface. What all we did in this, that we also measured the displacement, amount of displacement between different units, and that also helped us in understanding that what we see there. For example, we are looking at here in this play, the displacement of unit B is almost like 170 centimeter. This we have taken into consideration the outer boundary, this one here and this point here. So of almost like 170 centimeter, and then further we have marked the contact, that is we have considered either the upper bounding surface or the lower bounding surface of the respective unit. So here what we are looking at, the lower bounding surface of unit D, for example, to see this displacement, then we took this part and then this one here, which shows the displacement of almost like one. This is the tip we have considered, and this one the edge here. So this gave us a displacement of 110 centimeter, and then more to like 35, 40 and 25. Now with marking this all displacement, along with that we also measured in the field the dip angle of the fault strength here. Both the fault strength dip angles were been measured, and then the samples were been collected keeping in mind the hanging wall and the foot wall. Okay, and then again when the events were been fixed, for example, which were because this shows the maximum displacement, of course, then this becomes the unit which was displaced at least for more than 2 events. Okay. And this one is showing the maximum displacement, which we were not able to figure it out because we don't have the same unit on the footwall side. Anyway, then what we also interpreted here, that this unit C did not get displaced along this strand. So this is sitting away from the deformed area, and on the footwall. So let's see that what all the edges which we have we found here will tell us in terms of the bracketing the events. Now the best way is that we usually take that suppose this is the unit here, and the edges which are also been calibrated edges and calendar years we have given here in AD and BC so we have the OSL edges, we have carbon edges over here. Now we will take, if this is the event horizon and this was displaced at the time of earthquake, then what we will do is that we will take the minimum age of this unit, that is the last depositional age of this unit we will take or if we are having the charcoal, then we will take the youngest age of this particular unit, and then the oldest of this unit, because this is capping the, so minimum and maximum of this, and that will allow us to bracket the event. Now for example, this ages of this unit, that is unit D, what we have is AD 40 to 80, and then you are having 1200 to 1300, and then you are having 1200 to 1300 here. So we can consider one of the age from this, because this will become the older age, but this is the comparatively younger age, and this is more younger. So we'll take this age as the minimum age of this particular unit D. And similarly, if you have the age of unit E, in our case we were unable to find any effective sample from this. So what we did was we considered the age of the immediately overlying layer, that is unit F. So the minimum age of unit F, because that what we want to say that this was the capping unit, and this was deposited after the event. So that younger age of this one we will take, and sorry, the oldest over the oldest age, okay, because the younger age will not allow, younger age will be on the upper side, so we'll take the older age of this one. So minimum age of this and maximum age of the overlying unit will take, and that will allow us to bracket the event. Now let's see further how we have interpreted this trench in particular. So based on our interpretation using all the cross-cutting relationship along the fault and different fault strengths and the ages, we interpreted that at least 3 events have occurred along, we were able to identify at least 3 events along the Kaladungi fault. That is an imbricated fault of HFT. So we say that the displacements during paleo earthquakes and the event chronology suggests that the total 3 events have occurred along F1 and F2 strands. So at least 3 events have occurred along F1 and F2 strength, and out of this 3 events, two events have occurred along F2 and 1 event, which was the older one, along F1. So most movements during the paleo earthquakes have folded, okay, and faulted all litho units along F2 and its subordinate faults, which we were F2A and F2B. So you have F2A here and F2B is this one. So what we see that it has just not displaced the units very sharply, but it has also resulted into a major folding here. So this was again a very important like observation which we were able to identify from the trench log. I'll explain this. So this is typical of what we were looking at, the sandbox model, that if you're having a low angle fault which is bending close to the surface, then you will have the fault propagation folding along the tip of the fault. Okay. So this was a typical folding we see. Now unit A, which is the oldest one, okay. Unit A is the oldest one, was displaced during all events. So that means it got displaced along F1 as well as it got displaced along F2. So this is stratigraphically this is the oldest one. So it was displaced along during all events, right from event 1 to event 3 along F2 and F1. Now all units from A to F except C were displaced, because C, as I explained, that C was lying far away and the footwall from far away from the deformed zone in the football area, hence it was not affected. Now unit B and D, so if we take unit B and D, so you have unit B and unit D as this one, were displaced twice, and that was along F2 during event 2 and 3, because if event 1 was along F1. Now we are talking about event 2 and 3. So these two units were displaced twice, and they show a cumulative displacement of 170 centimeter. This is what it comes here, 170 centimeter. So they were displaced twice, whereas unit D display a total displacement of about 110 centimeter along F2. So this what we saw is that it is displaced 110 here, and the rest has been consumed along the F2A. So this around 40 centimeter was been consumed. So this becomes more or less similar to what we see here actually. So around 40 to 50 centimeter along F2A, and this was for unit D. So unit E and F were displaced once with a slip of about 25 to 40 centimeters. This has been shown here. So E and F, this is also got, it is displaced, and this during this event, this unit F was also displaced in this one. So unit E and F were displaced along F2, and about 40 centimeter along. So even E was displaced about 40 centimeter, very much similar to this, along F2A. So this was displaced along F2A here, and then 25 to 40 centimeter, which we see here along F2. Now this, since there is no displacement which has been taken up by the capping unit E, so we say that this was the most younger event, okay, or we can say most recent event, MRE. So for calculating the geometrical parameters, what we did, that we considered the slip 1, folded and displaced litho units along F2. So we wanted to go back into the deformation pattern and reconstruct that how the deformation exactly took place. So we used a cumulative slip of 170 centimeter of unit B to calculate the geometric parameters. So we used a very simple trigonometry here, like for considering you have the fault angle here, and then simply we are using the trigonometry in that sense, and then the angle which we took was around 25 at an average angle of this one, and this you will get by when you measure the dip angle in field. So this we consider 27 degrees, and the total slip of 170 centimeter, vertical separation which gave within simple trigonometry around 76. So this we considered, and we obtained using the angle and the slip, we got 76 centimeter of vertical displacement. That is your this one, okay, and slip you are taking here like 170 centimeter here, and theta you are taking around 27 degrees. So the vertical separation of unit B observed in trench was 215 centimeter. Taking into account the vertical separation of 215 centimeter and the theta 27 degrees, gives a higher slip of almost like 477 centimeter. But actually the slip what we obtained was 170 centimeter. So this is almost 300 centimeter higher than the actual slip what that we measured in trench, that was 170 centimeter for 2 events, because this is showing in cumulative slip. This 170 is your cumulative slip. So the net slip of 235 centimeter approximately can be accounted for a single event, because if we take this as the two event slip, then for single event this will be around 235. Also, the wide zone of deformation suggests that 60% of slip is consumed in folding, because we are unable to see this slip in trench. But if you just take the cumulative slip, then it is 170, whereas the cumulative slip, if we talk in terms of the slip using the vertical separation, then we should have seen this slip of this much, okay, 477. So almost like 60% of the slip has been consumed by folding. So this is very important when we talk about the slip rate, or we talk about the magnitude and all that, okay. So actually the slip would have been, or would have occurred much larger than what we have measured in the trench. So the rest of the slip was consumed along the by folding. So with this you can recalculate and go back into the like history and talk about the different events and how many events and what was the slip during single event. And if you are unable to fix up the slip, you will have to look for the other explanation, as the explanation we looked for that the 60% was been consumed by folding, and not everything was been seen as a part of the slip. Then further, with the help of ages, and you can fix up the events and go for a retro deformation sketches which we have prepared here. So what we say that the event 1 took place, okay, and displays unit A along F1 and F2, and that was the event, and then that what bracketing we have done. So it was during BC 467 and AD 570. So now considering all the parameters here which we have discussed, that you have the cumulative displacement, if you take the angle of the average angle of the fault and the ages, you can reconstruct the events chronology, and this was been done using Oxcales, the calibrated ages which you see here, and the bracketing you got from the Oxcale. But I'll just explain that how we have reconstructed the history here, and then we'll come to the bracketing part in the next slide. So what we inferred that event 1, it displaced unit A along F1 and F2 strands. So we see here, and then there was a phase of deposition which deposited unit B, C and D, and after this there was an event which again displaced F1 and F2, and displaced all the units which were deposited along with the older one, that is your unit A. And then there was a phase of deposition, that is your unit F, which capped the unit E and F were deposited after the event which took place, and this was the event horizon. So this and after the deposition of unit F, there was a final earthquake, that is your most recent earthquake. So now in this one, what you can at least talk about, that the event 1 took place after the deposition of unit A and before the deposition of unit B, and in this case the event a second event took place after the deposition of unit D and before the deposition of unit E. And finally what we see here is that the event 3 was after the deposition of unit F and before deposition of unit G. So if you are having the age, that is the older age of this one, the oldest or the maximum age we can say of the capping unit, and the minimum age of the event horizon, then you will be able to bracket the event. So what we inferred that the event, the second event, event 2, was bracketed between 1294 AD and 1587, and most likely we correlated this event with 1505, and this is well recorded event in historical data. Similarly, our youngest age which we got, we bracketed this event, and that was between 1750 and 1932 AD, and if we correlated this event with 1803, but there are like other groups who have worked, and they said that probably there was no such event which was recorded in their trench. Possibly they were not able to pick up this because the deposition of the units will vary from place to place, and we may not be able to see the same events in single trench. So ideally what we do is that we open multiple trenches in close by and try to understand that if there is the same event has been picked. Sometime we will not be having the same event picked up from both the trenches. So this is because of the variation in the depositional pattern, that is sedimentary phases will not be the same all along the scarp, and they may vary, and some places if this units are eroded, then you will not be able to pick up the events. Nevertheless, at least we were very confident about this event, that this has occurred along this fault, and this is one of the largest earthquake which has occurred in this region during historical times. So this is what we used the aux scale, and we calibrated all our ages, and we tried to mark the or bracket the different events which we based on the ages which we got from different units. Okay. So this what we say that event 1 here was, so we infer at least 3 earthquakes along Kaladungi fault, event 1 which occurred. So based on this we were able to bracket the event here. So we say that the event was bracketed between this 2 ages. So we have the 467 and 570 which is coming from the aux scale model, and then we have the event 2 was between this here. So we have the wide range which is between this and this. So we have like it is 1294 and 1587 which probably corresponds to 1505 earthquake in this region. Event 3 which I told that this is the debatable event, but what we saw in our trench we have correlated with 1803, and this was the youngest most recent event in this region. So I'll stop here and we'll continue in the next lecture talking more on the strike slip fault. Thank you so much.